we now begin the topic of functions, but really it's a continuation of the very end of our discussion of relations. So if you didn't watch the last video on relations, which is the one based on section 16.6, you should go back now and watch that, because what we're about to do is not going to make so much sense before you've seen that. All right, so let's define what a function is. Now, of course, you've seen functions many times already in many different courses, presumably, but we're going to maybe give it a slightly maybe more technical definition. Maybe you've seen it before, maybe not. So suppose we have two sets, A and B. So a function always starts off with sets, A and B. And we have a function f from A to B. Okay, so we talk about a function from one set to another set, and we denote it like this, right? This says f is a function from A to B. So this is a relation from A to B. In other words, f is a subset of A cross B. So every function has to be a relation from A to B. So it's a subset of A cross B. And it has to satisfy the following property. In order for it to be a function, it must satisfy this property. And here it is. For each little a in big A, meaning for each element of set A, f contains exactly one pair of the form A comma B. Okay, we'll see many examples of this, and we'll clarify this definition. So just a bit of notation here. If f is a function and we have a pair A comma B that is an element of f, again, remember, f is a subset of A cross B. So the elements of f are going to be ordered pairs. So suppose we have an ordered pair A comma B, and it's an element of f. We can write this as f of A equals B. And this is the standard notation that you've seen for a long time in writing functions. So for example, consider the familiar function from the set of real numbers to the set of real numbers defined by the rule f of x equals x squared. So what does that say? So the intuition here is that the inputs come from the real numbers. The inputs to the function are real numbers, and the outputs are also real numbers. And the function has the following rule. If you give it an input x from the real numbers, it will give you as output x squared, which is also going to be a real number. Now, for example, what is f of 2? Well, f of 2, well, the rule says do x squared. So we can, f of 2 is 4. 2 squared, which is 4. F of negative 2, that's going to be negative 2 squared. That's also 4. How about f of 2.5? So that's 2.5 squared, which is 6.25. 6.25. Now, if we want to write f as a set of ordered pairs, how can we write it? Because as we are saying, really, f is a set of ordered pairs. So we can start writing it like this. F, of course, it's an infinite set. We can't list out all the ordered pairs, but we can list out some, right? So we have the ordered pair 2, 4, and the ordered pair negative 2, 4. Again, because we know that f of 2 is 4, we write 2, 4 as a pair. And since f of negative 2 is 4, we have the ordered pair negative 2, 4, and so on. But of course, this is not really the correct way to write it, because it's not so obvious from what we have here exactly what the function, what's included in the function and what's not included in the function. Right here, we're just giving some examples of things that are in the function, but it's better, well, not just better, we need to be able to write this function in a way that's perfectly clear about which pairs are part of the function and which pairs are not part of the function. So we know already that it's a function from the real numbers to the real numbers. So that means all the ordered pairs are going to be made up of real numbers. But we want to be more specific than that. So here's as specific as we can get. It's the set of all ordered pairs, x, x squared, where x has to be an element of R. But this applies to all x in R. So if you take any x in R, every single possible value of the real numbers, we'll call it x. If you have an ordered pair x, x squared. Of course, you have infinitely many such ordered pairs. F includes all those ordered pairs. It's a set containing all those ordered pairs. Now, of course, you must have learned many times by now, you must have seen many times that you can actually draw a graph of this function. Okay, you can draw a curve representing this function. So what we have here is, the x-axis and the y-axis. But here, the point is we have real numbers as inputs, right? And real numbers as outputs. So the x values you can think of as the inputs. What you would call until now is the x value are the inputs to the function, and the y values would be the outputs of the function. And this curve here tells you which things are in the function and which things are out of the function. And here's what I mean. Each point on this curve, right? This curve is made up of infinitely many points. Now, each point on this curve represents what happens when you have a specific input of x, and then you have a specific output of x squared. So, there's one point over here. I don't know exactly where on the curve it is, but there is going to be a point on this curve, 2, 4, right? Like this, 2, 4. There's going to be another point on this curve, -2, 4. There's going to be another point on this curve, 2.5, 6.25. In general, every point on the curve has the form x, x squared. So this entire diagram, right, and really it should really extend to infinity in all directions. But this entire diagram is R cross R, right? It's the Cartesian product of R with itself. Right, every single point on here, not just on the curve, every single point in this gray area and really extending beyond in all directions to infinity is an ordered pair of real numbers. But not all those ordered pairs are part of the function. The function only includes the ordered pairs that are on this curve, the points that are on this curve. Okay, great. Let's we'll see more, of course, we'll see more examples of functions, but before that, let's introduce some more definitions. And those are domain, codomain, and range. So suppose we have a function f from a to b. So it's a function from set A to set B. The domain of f, I'm sorry, I'm missing an f there. So the domain of the function is this set A. Now, to be more specific, the domain contains all the inputs for f, right? So this the idea of inputs is the intuition. It's not a very precise idea, but the inputs to the function, things that go into the function and get processed by the function. So it contains all the inputs for f and nothing more. So that's very important. The domain has to contain all the inputs of the function, but nothing more. The codomain of f is this set B. It contains all the outputs of f, but it possibly can also contain more than just the outputs. So it's allowed, the codomain is allowed to contain more than just the outputs of the function. It has to contain all the outputs, but it is allowed to also contain more things. The range of f is the set of all f of a such that a is an element of the set A. In other words, the range is the set of all b such that there is a pair a comma b in the function f. In other words, it contains all the outputs of f, but nothing more. So notice the range and codomain are similar ideas, but not exactly. They both have to contain all the outputs of f, but the codomain is allowed to also contain additional items, whereas the range only contains the outputs of f and nothing more. Now let's look at some examples and talk about these definitions. So here is our example from before. So again, consider the familiar function f from the real numbers to the real numbers defined by the rule f of x equals x squared. So what is the domain of this function? So the intuition is, what are all the possible inputs to the function? Well, we are told that it's a function from the real numbers to the real numbers. So this thing has to be the domain. By definition, this is the domain. So the domain of f is a set of real numbers, R. The codomain of f is also the R, the set of real numbers. What is the range of f? So the range is the set of all possible outputs, but nothing more than that. So we cannot say that the range is R because, for example, there is no way to get an output of, let's say, -3 or even -4, right? There's no way to get an output of this function to be -4. In general, well, more generally, there's no way to get any negative number as the output. Now, it's possible to get any non-negative number as output. And you can see that really from the graph, right, from the curve. So if you think about y values, right, from like a pre-calculus or a calculus class, what are all the possible y values? Well, the smallest possible y value is 0. And then after 0, you can have any real number starting from 0 and going to infinity is a possible output of the function. So the range of f is the interval of real numbers starting from 0, including 0, all the way to infinity. Let's do another example. Consider the function g from the set of integers to the set of natural numbers defined by this rule. G of n, so n is going to be an integer, and now we're going to say what to do with that integer. So n is our input, and then this is the output. So g of n is equal to the absolute value of n. Okay, this has to be absolute value because n is not a set. So obviously this is not cardinality. It has to mean absolute value. So absolute value of n plus 2. So let's write g as a set of ordered pairs. So for an input of 0, we're going to do the absolute value of 0, which is 0 plus 2. So we get a pair 0, 2. Again, for an input of 0, we have an output of 2. For an input of 1, we do the absolute value of 1 plus 2, so we get an output of 3. For an input of -1, we do the absolute value of -1, which is 1, and then we add 2, so we get an output of 3 again. And so on. Of course, this is an infinite set. We can't list out all the ordered pairs. Why? How do we know that we can't list out all the ordered pairs? Because the domain is z. So that means that that every single integer is a potential input to the function. So we can't list out all the possible values, right? We can't list out all the possible ordered pairs because we wouldn't be able to list out all the integers on the slide. Okay. More generally, we can write this function as follows. It's the set of all ordered pairs of the form n, comma, the absolute value of n plus 2, where n is an element of z. Right? So it's like for all elements of z, make an ordered pair n, comma, absolute value of n plus 2, and put that into the function. Let's see a diagram or a graph, if you would like to call it that, of this function. This looks a little strange. You don't see a curvy line. You don't see any line at all, actually. What you have here is this, you usually call it the x-axis, but there's no special reason to call it x. In fact, here it's the n-axis, if you want to call it anything. But it's the point is the input, it lists out, it represents the possible inputs. And then this direction represents the possible outputs. Now the inputs could be any integer, right? Because this is the function from z. The domain is z. So the input could be any integer. So -4, -3, -2, -1, 0, and so on. And of course, going on in each direction. And then the black dots, the filled in dots, represent the points, are the points that represent ordered pairs. So for example, we have this point here represents the point 0, 2, right? So for an input of 0, we get an output of 2. For an input of 1, at this point here, there's an input of 1, we get an output of 3. For an input of 2, we get an output of 4. For an input of 3, we get an output of 5, and so on. For an input of -1, we get an output of 3. Of course, okay, great. So the domain of G, as we said, is the set of integers. The codomain of G is the set of natural numbers, n. What is the range of G? So the range of G, so you might say, well, it's n, but if you look carefully at the graph, or if you think about it, there is no way to get an output of 1. But after 1, starting from 2 and going on integer to integer to integer, you can get each of those integers as outputs, right? So you can get an output of 2, you can get an output of 3, you can get an output of 4. Actually, there's more than one way to get an output of 3 or 4. You can get an output of 5 in more than one way. At any rate, the range of G is the set 2, 3, 4, 5, all the way to infinity. Now it's now we're going to talk about we're going to really go back to our definition, our original definition of function, and hash it out a little bit more, because we started by saying that every function is a relation from A to B that satisfies the property that for each little a in A, f contains exactly one pair of the form A comma B. Now, let's look at some examples of things that are definitely relations from A to B. And what we'll try to do for each of them is determine whether the relation is a function. All right, so many relations are not functions. Many relations are functions. So we'll try to determine that. So let's say we have the set A, which contains P, Q, R, and S, and the set B, which contains 0, 1, and 2. And now I'm gonna show you a relation from A to B. It's definitely a relation, no question about it. It's going to be a relation from A to B. The question will be whether that relation is a function. All right, so here it is. We'll call it f. We can call it whatever we want. Just because we call it f doesn't automatically mean that it's a function, although usually we use f to indicate a function, but it doesn't have to mean that. It's just some name that we're giving to a relation in this case. And as usual, a relation from A to B is a subset of A cross B. So that means we have some ordered pairs where the first element of each pair comes from A, and the second element of each pair comes from B, so like the 0 and the 2 and the 1 and the 1. And we would like to know, is this relation a function? So in other words, we want to know, does it satisfy the property that we have here in the definition of functions? So what I'm going to do next is show you one way of drawing this function in a diagram. And of course, as you'll see, this diagram only works for very small little functions like this. Like you can call them toy functions if you would, but they're not really useful. But they are nice little diagrams that help illustrate some points. So here we have a set A, P, Q, R, and S. Here we have a set B, contains 0, 1, and 2. And now here's the function f. The function f is represented by these arrows. So when there's an arrow from P to 0, that corresponds to the ordered pair P comma 0. There's an arrow from Q to 2 that represents the ordered pair Q comma 2. There's an arrow from R to 1 that represents the ordered pair R comma 1. There's an arrow from S to 1 that represents the ordered pair S comma 1. Okay, so this is a nice little diagram. We would like to know, is this relation a function? So what do you say? Yes, it is a function, since for every little a in set A, there is exactly one pair of the form A comma blah, whatever. Meaning we have 4 different values of A, P, Q, R, and S. For each of those 4 values, we have an ordered pair. So we have P comma something, Q comma something, R comma something, S comma something. It doesn't matter what's in the second part, but the point is for all of the values of A, right, for each little a in set A, f contains exactly one pair of the form A comma B. Let's look at another example. All right, so again, same set A and same set B, but now we're going to have a new relation, and we're going to want to determine whether it's a function. So here's the relation f, call it f, Here's a diagram of the relation. And now we would like to know, is this relation a function? And the answer is no, it is not a relation. It is a relation. I'm sorry, it's not a function. It definitely is a relation. Why is it a relation? Because it's a subset of A cross B. But it's not a function because it doesn't satisfy this property here, because there is no pair of the form R comma something. Right? So you can see here in the diagram, R has no arrow coming out of it. Or you can see here in this set of ordered pairs, there is no pair of the form R comma something. So therefore, it's not a therefore this F, even though it's a relation, is not a function. Here's another example. Again, the same sets A and B, and now we have a new relation, again called F. And here's the diagram of the relation. And we would like to know, is this relation a function? The answer is no, it's not a function. But here it's a slightly different reason. Here, the reason it's not a function is that there is more than one pair of the form P comma blah, meaning we have P comma 0 and P comma 1. Or as you can see in this diagram, P has two arrows coming out of it. But the property of functions tells us that for each element of A, F must contain exactly one, not more than one, not at least one, exactly one pair of the form A comma B. But here there's more than one pair of the form P comma something, meaning so there's P comma 0 and P comma 1. So therefore this F, even though it is a relation from A to B, it is not a function. Another example, let's say we have a function, we have a relation here, another relation F. Here's the diagram of F. So the question is this relation a function? So you might say, well, here we see 2 all by itself. There's nothing pointing to 2. So does that violate the property of functions? Or maybe no, or maybe it is still a function. Well, the answer is it is a function. It is a function. Because again, the property says for each element of A here is the domain, right? Not B. B is the codomain, but we're talking about A. For each element of the domain, F contains exactly one pair of the form A comma B. And that's true. A contains exactly one arrow coming out of each of these elements in A. Now, even though there is an element of B that has no arrow going to it, that doesn't matter. That's still a function. F is still a function. All right, great. Now, quick little definition here. Function equality. Let's say we have two functions, F from A to B and G from C to D. We would like to know whether these two functions are equal to each other. So how do we define function equality? So functions F and G are considered to be equal. We need two things to be true. First of all, we need to make sure that A is equal to C, meaning even though A and C are different names, we need to make sure that they're actually equal to each other. Meaning we need to make sure that these two functions, F and G, have the same domain. Now, they don't have to necessarily have the same codomain, right? So it's not necessary that B is equal to D. It's fine if they have different codomains, but they must have the same domain. So A must be equal to C. And in addition, F of A must equal to G of A for every element A of set A. Okay, so meaning for all possible inputs to the functions, the outputs have to be the same. F of A must always equal G of A. So for example, the following two functions are equal. So here we have a function F from the set of from the set of integers to the set of natural numbers, defined by the rule F of n equals absolute value of n plus 2. We've seen this before. Here's another function, which we'll call G. Here it's a function from Z to Z. Notice the codomains here are different, but there's these two, but functions F and G are still equal because they, first of all, they have the same domain, and we also need to make sure that they always have the same output. Well, here G of n is given by the rule the absolute value of n plus 4 minus 2. Well, that's really just the same as absolute value of n plus 2. So the outputs of these two functions are always going to be the same, no matter what the inputs are. And as we pointed out, the two functions have the same domain. So therefore, these two functions are equal.